everyone, welcome back to the video lectures on image and speech processing. So we have been talking about what is the basics of image processing, image sampling, quantization. Then we talked about different pixels relations, right? So in today's class, in today's video lecture, we would be talking about the image enhancement techniques. In my previous video, we were talking about the image enhancement techniques using intensity transforms. So we learned about linear, logarithmic, power, right? Piecewise linear. How are they useful? How are they even useful for image compressions? So here today we'll be talking about the image enhancement techniques. The other techniques where we will have an image enhancement, right? So in today's class, we'll be talking about histograms, right? Histogram and histogram equalization. So what actually is histogram? When we have an image, say suppose f of x comma y, then I have a matrix which is say suppose 24 cross 24. I will have all my intensity values. What are we trying to do is, if my r of k, where it is the intensity value representation, okay, say suppose my rk is equal to 3, okay, then I am counting how many number of pixels are having the same intensity value 3. I am counting the number of pixels which are having the same intensity value 3. That is called as the unnormalized histogram of the function or the image f. Right, so I'm counting each and every intensity value and I'm saying what is the count number. So if I say R1, R0, where k is equal to 0, then I'm counting how many pixels are having the value, intensity value to be 0. So like that, this is my generalized equation by which I can represent my unnormalized histogram. So unnormalized histogram is basically the count of the number of pixels that are having same intensity value. Whereas we go for the normalized histogram. Okay, so what am I trying to do here is the unnormalized histogram by the total number of pixels in that image. Say if my f of x comma y is of m cross n size, then this will give the result for my normalized histogram. So this is otherwise in other terms we can say the probability. Right? We can say that this normalized histogram is representing my probability value. Right? So this can be used for calculating the probabilities of a histogram, probabilities of the intensity values, which we will see in the problems dealt, and as well as it is very useful for image compression models also. Right? So why are we going for histogram is, basically histogram is very easy to compute. It is an important tool. Why it is important means it is easy to compute and less computational overhead is observed. Right? Less computational overhead is observed. So because of these two reasons, it is an important tool, and using this also we are able to achieve a image enhancement. So it is a very easy task of counting how many pixels are having the same intensity value. So histogram is a very important tool that we are going to use it for my image processing techniques. Right? So based on my histogram, I can divide the images into 4 types. Right? So there are 4 possible types which can be divided or identified based on my histograms. The first one is the dark image. Second one is the light image. Third is the low contrast image and high contrast image. Okay, so how did I differentiate? How is the histogram differing means? If I have a dark image, all my histogram plots are concentrated towards my left side of the plot, and as well as the bandwidth or the range of the intensity values occupied by the histogram plots is very narrow. Right? So when we go for my light image, the histogram is obtained the histogram plots are at my right side end of the histogram plot, right? So here dark and light image can be differentiated also based on my histogram plots. My dark image will have the histogram plots on my left side, and the light image will have the histogram plots on my right side, right? Now, what is a low contrast and high contrast means? All the histogram plots are centered, are at a one particular point, and the bandwidth occupied by these plots, the bandwidth occupied by these histogram plots is very narrow. Then such kind of a image is called as my low contrast. Whereas when we go for a high contrast image, what is happening is histogram is uniformly distributed all throughout my intensity range, right? So if I plot my histograms where on my x-axis I have the R value, which is the intensity value. On my y-axis I have the count, right? So if I have plotting the plots and it is like uniformly distributed all throughout the intensity value. Say suppose my possible values are 0 to 255 and I have an image which is ranging from 0 to 255. Every pixel value is having a range between 0 to 255 and it is uniformly distributed, then such kind of an image is a high contrast image, right? So based on my histogram I can divide it into 4 parts. One is the dark image, light image, low contrast image and high contrast. High contrast image is the most important image type, right? Now, so what is here is a image that has a uniform histogram. They tend to occupy the entire possible intensity levels. It is a high contrast image, right? So we want in real time applications, we want all the images in high contrast images and important, like when we go for medical, we go for satellite communication images. Okay, for all those cases high contrast image is an important point. So if we have the four types of histogram, we need to convert all the three types, which is like dark image, light image, low contrast image, to a high contrast image. We need to convert all these three cases to my high contrast image. So that conversion is converted, or this conversion is achieved using a histogram equalization. So what are we doing in histogram equalization is we are converting the input histogram. Okay, we are converting my input histogram, which can fall in either of these three cases, to a uniform histogram. So this process is called as my histogram equalization. So using the histogram equalization process, I can achieve a image enhancement. So basically, when we see a image, if we go for a histogram plot, we can clearly differentiate what kind of a image it is, whether it is falling under a dark image, low contrast image, or light image, or a high contrast image. If it is a high contrast image, then it is very much useful for my applications. If the histogram is depicting the other three cases, then we need to perform this histogram equalization so that it gets converted into a high contrast image and it is useful for our applications, right? Now, how do we do this histogram equalization? What are we going to consider is, there are few assumptions that we are going to do. So, we are going to assume that input intensity values, which are represented by R, which are belonging to the range 0 to L minus 1. Okay, here R means it is a black color, L minus 1 means it is depicting the white color. So, all the intensity values are falling in between this range 0 to L minus 1. So this R is equal to 0 means it is black, R is equal to L minus 1 means it is falling as white. Now, what are we doing is, if S is the output intensity values, then S is equal to T of R, where R is falling in between 0 to L minus 1. So, we are doing some operation T on my input intensity values R to get an output intensity value S. Here, what are the conditions that are to be followed while choosing the transform function? We cannot choose all the cases. all the transform functions, there are some conditions to be followed. What are those conditions is, it should be a monotonically increasing function. The transform function should be a monotonically increasing function in the interval 0 to L minus 1, right? And if R is falling in the range between 0 to L minus 1, and then S should also fall in between the range 0 to L minus 1. That means if I have a gray image and its intensity values are from 0 to 255, after doing some operation, it should also be a gray image. My output should also be a gray image, and all the intensity values should fall between 0 to 255. If we are performing some operations and this gray image is getting converted into a color image or a binary image, then such operation is not called as my histogram equalization. So what basically is that, if R is falling between 0 to L minus 1, then S also should fall in the range 0 to L minus 1. And the function should be a monotonically increasing function. And that too in the same range 0 to L minus 1. There are two cases where the function can be monotonically increasing function and can be represented as shown here, this A and B parts of my figure, right? So let's consider here, if my function, which is my transform function, it is monotonically increasing as shown in this A part. Okay, now when we try to reconstruct back my original image from my output image, okay, so when I apply this is my transform function, S is equal to T of R, right? So if I want to obtain my original intensity values from this output intensity value, then how do I get T? T is equal to, R is equal to T inverse of S. Right? So what does this mean is, I am doing an inverse operation on the output intensity values S to get my input intensity value. Now let's observe the same thing for my graph A. Here, if we observe, I have a section where it is a constant for a range of the intensity values. What does that mean is, for this range of R values, we have mapped, or we have got the output intensity value to be SQ, right? Now, from SQ, when I'm trying to calculate back my original image using this equation, when I'm trying to calculate them back, so if I have this SQ here, okay, SQ of value, say suppose 10. So this 10 is mapped to which range of S, which range of R? What is the actual value of R? So we are not able to differentiate because we have multiple R's mapped to a single value. So which creates an ambiguity. This creates an ambiguity. So whereas when we go for the case B, we are having a one-to-one correspondence. We are having a one-to-one correspondence between between R and S. So this is called as the strictly monotonically increasing function. So that is why for a histogram equalization to happen, we need a strictly monotonically increasing function. So this T of R, or the operation T, which is to be monotonically increasing, now changes to strictly monotonically increasing function, and the S value should also be in the range of R. If R is ranging between 0 to L minus 1, then S also should fall in the same range, which is 0 to L minus 1. Right. So if we are saying here R is a random intensity value, right? So R is the intensity value of an image, input image, right? It is the input image. It is falling in between 0 to L minus 1, but it is also a random variable. Okay, it is a random variable. Then let this PR of R denote the probability density function, PDF of the values R, right? So this PDF is being represented as PR of R. Now using this probability, and we are using this probability theorem. Okay, now what is the probability theorem is, if the probability of the PDF of the input intensity value R and the transform function or the operation T are known, and they are also continuous and differentiable functions, then the probability transfer function S can be given, or the probability density function of my S output intensity values can be given by this equation. Right, so the probability density function of my output function is dependent upon my probability density function of my input intensity values, and also on my transfer function, which is represented by dr by ds. Okay, so if we know the probability density function of my input intensity values, I can obtain my probability density functions of my output function by this equation. Now, let's take one example of the transform function, like the transform operator that we are going to do. Let that be a cumulative density function. Let it be the CDF function. So that is given by S is equal to T of R, which is equal to L minus 1 into integration of 0 to R PR of W into dW. So this is my equation for my cumulative density function. Okay, and we are assuming that my transform function is my CDF, right? So before we go, how is my histogram equalization condition is obtained, I am going to check, we have to check whether the conditions on my transform function are met or not. How do we do is, now CDF or the cumulative density function is basically the area under the function. Area under the graph. Say suppose this is the graph, then the area covered by that is equal to my cumulative density function. Now, this area is always an increasing function. Okay, it is an increasing function. Area function is always an increasing function. So we can say that the transform function is a monotonically increasing, strictly monotonically increasing function. Now, the other condition that if R is falling between the range 0 to L minus 1, then S should also fall in between 0 to L minus 1. Now, how is that condition satisfied? Is the maximum value of this cumulative density function can be 1, is equal to 1. Right, so the input probability value is S is equal to L minus 1 into integration of 0 to R and the probability value dW, right? Now, if this value, maximum value is 1, then what is happening here is the S max value is equal to L minus 1, right? Now, if this function is having a minimum value to be 0, then minimum value, it has the minimum value to be 0. So this whole S minimum now becomes, S minimum will now become to 0. So if R is equal to, if R is equal to 0, then we get S minimum which is equal to 0. If R equal to L minus 1, then S, we get the S max which is falling in between L minus 1. So S is falling between the range 0 to L minus 1. So this condition of the transform function is also satisfied, right? Now, how are we going to calculate the probability density function of the output image? So how are we going to do is, S is equal to T of R equal to L minus 1 into integration of 0 to R PRW into dW, right? So here, what are we trying to do is, S is given as this. Now, what is the probability density function given by equation is equal to probability of the output function is equal to probability of the input function into modulus of dAR by ds, right? So this was the equation. So we have to calculate this part. So how are we going to calculate this? We are going to first calculate ds by dr, which is equal to d by dr of T of R. So that is given by d by dr into L minus 1. We are substituting this value T of R from here, which is equal to L minus 1 into integration of 0 to R PW, PR of W into dW. Now, L minus 1 is a constant, so we can just remove it outside my derivative. So, d by dr of integrated 0 to R PR of W into dW. Now, we are going to use this Leibniz rule to calculate this value. Now, what is this Leibniz rule means? The derivative of a definite integral with respect to my upper limit is equal to the integrated value at the upper value. So, what does that mean is, let's go back here. So, if I am doing a derivative of a definite integral, I am performing the derivative. So, this is the derivative of a definite integral because it is a limited value which is ranging from 0 to r. So, it is not ranging from minus infinity to infinity, or it is not like just left without any limit. So, it is a definite integral, right? So, a derivative of a definite integral is performed. Now, definite integral, now how is the derivative performed? With respect to the upper limit. So, the upper limit is r here. The derivative is also performed with respect to r. Then, so this condition, if this condition happens, then what is the value? If this derivative happens, it is equal to the integrated value at the upper value. So, what does that mean is, this is equal to, this whole equation is equal to PR of R. Right? So, we got as the derivative of S with respect to R is equal to, the derivative of S with respect to R is equal to L minus 1 into PR of R. Right? So, we get ds by dr is equal to L minus 1 into PR of R. So, if we try to calculate this probability density function of my output image, which is equal to PS of S is equal to PR of R into modulus of dr by ds. Right? So, we have got ds by dr equal to L minus 1 into P of R. So, I am taking the reverse operation. So, I get this is equal to PR of R by L minus 1 into PR of R. So, if I just subtract, this is equal to L minus 1. Right? So, this is equal to my uniform distributive function probability function. Right? This is equal to the probability density function of a uniform function. Right? So, this PDF is the output intensity value and it is uniformly distributed. Since the output intensity values which are represented by S are having the probability density function which is a uniform, histogram equalization is performed and a high contrast image is obtained. Right? So, this is the one example when we have taken this cumulative density function as my transform function. Right? So, we were able to achieve my histogram equalization and a high contrast image was obtained. Now, let's go here. Well, let's take a small other example where the probability density function of my input intensity values are given by here, which is equal to 2R by L minus 1 square. It is following the range 0 to L minus 1 and it is 0 for all other cases. Now, using this probability density function, we have to calculate the output image, right, after performing my histogram equalization. Now, how do I get my histogram equalization? Right. So, histogram equalization means S is equal to L minus 1 integration of 0 to R P R of W into dW. Right. So, this we are going to use and calculate for my output intensity value. So, for that, in my previous case, what did I do? I started calculating the function which is equal to ds by dr. Right? So, which is equal to ds by dr. Now, before we go there, let's substitute this value which is equal to S is equal to L minus 1 into integration of 0 to R to W by L minus 1 whole square dW. Right? So, this is my input function means I am representing or I am substituting in this equation. So, only for 0 to L minus 1 or 0 to R, this function is satisfied. So, L minus now is equal to I can subtract this. So I get 0 to L minus 1. Integration of 0 to L minus 1 to W dW, which is equal to, what is the integration of W? It is equal to 2 by L minus 1 into W square by 2. So which is equal to 0 to L minus 1. So I can substitute this, which is equal to L minus 1 whole square minus 0 by L minus 1. I get L minus 1 by whole square by L minus 1, which is equal to L minus 1. So from this we see that the output intensity value S is equal to this L minus 1, which is a uniform density function, right? So using my histogram equalization, I was able to achieve a uniform distributed function, which means that a histogram equalization operation is performed and a image enhancement is obtained. Okay. This histogram equalization can be used with respect to my images, specific images, to enhance my image pixel by pixel. So we can achieve a local histogram equalization. Though we can achieve the local image enhancements also. So this histogram is not specifically performed on my whole image. I can even perform on my segments also. So based on my requirement, I can go for image enhancement, localized histogram equalization, or the complete histogram equalization. Right? So this is the end of the video, and we can go for further knowledge in my Gonzalez books, which is the digital image processing by Gonzalez. So this is the more information can be obtained from this reference book. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.